Okay, so we'll do a little bit on conservation of energy and do some more on it today. Quick example, remember conservation of energy just says that the total energy of a system is constant. So the total energy of a system is constant. Any kinetic energies initial, any potential energies initial, or other energies initial. It could be thermal, it could be friction. It can actually be work done, and we'll get into that in a little bit. Equals the kinetic energy final, plus the potential energy final, plus any other energies. Basically, it's all accounted for. It stays constant. It's got to go somewhere. It gets shifted around, but it's going to be accounted for. Okay, and the easiest one, one of the simplest ones is pendulum. And we did the pendulum with the forces the other day, which was hopefully pretty cool in lab. But if you have just a simple pendulum here, and a mass on the end, then you bring it back to here, and you let it go. As you let it go, of course, it'll go here and here. Forwards and backwards, forwards and backwards. Now, what you can see is, if you notice that pendulum, when it's brought back and released, it's released at some height, h. So this is where it starts, and what I'm going to say, it finishes at the bottom. So it's fastest here at the bottom. So here, the velocity is 0. Here, the velocity is maximum. Now, from a pendulum's perspective, if it's just sitting here pulled back, if you just sit here and pull it back, it's not moving. So it doesn't have any kinetic energy. No. It doesn't have potential energy yet because it has the potential to swing. So if I pull it back, so at this point there is kinetic energy is 0, potential energy is maximized. So look here at the very bottom. I say it's got the maximum velocity because it starts going up, it starts slowing down. So at this very bottom, can it fall any further? From this perspective, that's the floor. You can't fall off the floor. So there's no potential energy right here. But the kinetic energy is maximized. It's going as fast as they can. And assuming no friction or no other energy, air resistance or anything like that bleeding out of the system, we can say then that the initial energy in equals the energy out. Or we can say the energy, which is conservation of energy, we just say that the energy at the top equals the energy at the bottom. So the energy at the top is no kinetic energy, but it is potential energy at the top. And that's going to equal, there's no potential energy at the bottom, there is kinetic energy at the bottom, so I'm just going to say kinetic energy at the bottom. Well, potential energy, and that's all due to gravity, no springs involved, that's mgh. We know the kinetic energy at the bottom, kinetic energy is moving energy, it's 1/2 mv squared. So if we want to find the height of it, how high does it go to be a certain velocity? Solve this equation for h. Or, if we want to know the speed at this point, solve this equation for velocity, and plug in the height. Because you notice, does the mass matter for a pendulum? And the answer would be no. No, it doesn't. Now you say, well, if I don't put anything there, it goes real slow. I said, yes, but that's air resistance, which we are not taking in this model. Remember, models are simplified versions of reality, and that's what we're doing, using a simplified version of reality to try to explain something. Okay? And that's really example 10.7. Now, they do ask a question, and the question they ask next is, okay, in that case, where is the potential energy? Where is that potential energy stored? Is the question. And I include this because the book did it. Really, it probably should have come later in my perspective, but the book asks the question, so let's talk about it for a second. When I pull it back, Where's the potential energy? First of all, what's causing that potential energy? What's pulling it down? It's gravity. Gravity is something known as a field. And we haven't talked about fields too much. We'll talk a little bit when we get to gravitational field. I think it's chapter 12 or so. But this field, this gravitational field, is actually where it's stored. In the field. Gravitational, in this case. It's gravitational in this case. And that's where that potential energy is stored. Gravity stores it, the field that's there, because the field goes, all right, I will store the energy, and as you let it go, the field kind of releases that stored energy. I think that's all I want to go down on here for now. What is a gravitational field? It's just how gravity affects everything around it. And when we get to electricity, later on we'll say that electricity, when we get to electric fields, if you take the next version of this course, 212, we'll show that in electricity and magnetism, the fields are where the magnetic energy and electrical energy is stored. In that case, it's stored in the field. That's an easier thing to explain than this one. But that's what the book has, so I want to go over it. They then talk about 10.5 energy diagrams. And these are similar to those bar charts they did earlier. But they don't just use bar charts, they also do it graphically. I guess what I'll say here is they're plotting. In the book, they plot energy on this axis, on the y-axis. They plot really position here. Then they, at the same time, they do kind of a bar chart with potential energy and kinetic energy. And like in this case here, where it's just really right there, it's basically zero. This would be a situation where something it's all potential energy and there's no kinetic energy. So what they say here is that the total energy of this system is constant. Total energy is constant. But they do graphs on potential and kinetic energy there. I'll be honest, I think this is the best way to explain it, honestly, with the graphs. Now, the bar charts, how potential and kinetic energy change in snapshots at a function of time. If I take this and throw it in the air, we can look at the energy of it right here. It's got a lot of kinetic energy, and really if this is zero, where I let it go, if I catch it at the same spot, it's got no potential energy. As it goes up, it's still moving, so it's got kinetic energy, but it's got less because it's slowed down. And it's got a certain height, so it's got some potential energy as well. As it goes up, it starts losing kinetic and gaining potential until at the very top, right at the instant that's at the very top, it's not moving, its velocity is zero, but it's got maximum potential energy. And all the kinetic energy here became potential energy at the top. So at the top, this would be at the top for a ball, or in this case a marker, tossed upward. Here, this is kinetic energy, this is potential energy. We'll say at the halfway point of flight. And then this one, this would be at the bottom of the flight like when I released it or caught it. And you say, well, how can that be the same kinetic energy? It's velocity squared, even though it's a different direction it's traveling. If I catch it at the same height I threw it, same amount of energy. The kinetic energy of it's the same because I didn't change the floor. The floor, which is zero of potential energy. So all that potential at this point had to be kinetic energy. All right. And that would be how it would switch over time. And of course, as this went down, the kinetic energy goes up. So as it falls, potential energy goes down, kinetic energy goes up. The other way, the kinetic energy goes down, and then the kinetic energy, as it rises, the kinetic energy would go down because it's slowing down, and the potential energy would go up. That's these energy diagrams. And that might be something I would ask you to draw on a test, to try, or maybe at different times in the motion of something, I could ask you to kind of use those charts to explain what's going on. They do talk a little bit about equilibrium positions, and I don't want to, and they talk about stable versus unstable positions. Now, let me give you an example of stable versus unstable. If I hang this right here, is it stable? If I had this kind of on a pivot, say I had a pivot like a piece of metal going between this expo marker to the other finger, and I was hanging it on that, it would hang straight down. Does it want to move anymore? No, it doesn't want to move. So when you think of equilibrium, we normally think of the forces are equal, so there's no net force on the system. From an energy aspect, when you have a stable position, that's when the potential energy is minimized. It's when the potential energy is minimized. Okay? In this situation, then, we're going to be minimum. So in this one, granted, it's going down, but from it rotating like this is the minimum potential energy. If I just let it go, it'll sit like a pendulum, it'll go this. But this isn't really a pendulum. This is like a stick as opposed to the string. Now, there is another equilibrium position for this situation, say a stick with a weight on the end. What if I could balance it like this? If I could see if I can bounce it on my finger. Oh, that didn't work. Try again. Bounce on my hand. Bounce on my hand. I am too hyped up today. Let me calm myself down. Do my yoga. Oh. All right. Breathe deeply. I'm relaxed. Won't last long. See if I can balance it now. A little bit better. Ha. I can balance it, but it's unstable. It doesn't want to stay there. Any little forces, any little motion of my hand to one side, it wants to lose potential energy and start moving, gain kinetic energy. This is an unstable position. Oh, look at that. Look at that. Just need to relax, right? Just need to relax. But that's unstable. This is stable. It has potential energy here, even though there's no net forces. So if there's any little force on it, it starts losing that potential that it has, because it still has the potential to move. Here, it's got no potential to move. There's no more extra potential. I mean, There's no potential energy there. So if there's a little bit of force on it, it doesn't have the potential to do anything. So this is what you call equilibrium. It's when the potential energy of the system is minimized. And that little dangling, stick with a rock on the end type pendulum, you can call it, is I think a pretty good example. All right, questions on that? Since this is a video, I doubt you don't have any. See, I'm so relaxed. Now. All right, let's stop that crap, right? Let's look at force and potential energy. This is 10.6. Force and potential energy. Now, we had said earlier that the work done, we're going to call that on this system, we're going to do work on a system so that energy leaves that system. And that's the force that system exerts to move something over a distance. And we're going to have these in the same direction. And since that's minus, so energy is leaving that system. S means it's in the same direction. So remember it was F dot dr. It's a dot product. And this just means they're in the same direction. Dot product is the magnitude of the two vectors times the cosine of the angle between them. If they're in the same direction, the cosine, the direction between them is 0. The cosine of 0 degrees, or 0 itself in radians, is just 1. So that's why there's no cosine there. We'll just write this in the same direction. Now, this work done is energy that left the system. It's not when Elvis leaves the building, it's when energy leaves that system. So, we think about it then, this work done, the force then, is going to be equal to this energy that left the system, the negative of that, because I've got to bring the negative over the change in position. Now, if this energy that left the system was energy that was stored in this system, that energy would be what? It would be potential energy. And that potential energy that left is actually the change in potential energy that that system had. The system had 50 joules work. It took 20 joules to move the papers around or something. Who knows? And that 20 joules of work that was done, now the system's got 30 joules of energy left because of conservation of energy. So the change in the potential energy would be the work done. That's that 20 joules. It'll be right here. So that the force it took to move something, to do the work, is equal to the change in potential energy over the change in the position. Now what's interesting with this, we can take in the limit. Why don't we let that change in position be really, really small? We let that change in the position be really, really small. And in the limit then, as delta S approaches 0 of the change in the potential energy over the change in position, that's a delta S. That's a triangle, it means change. Well, in the limit, as this gets really, really small, these deltas now, I can't really see that there's a change. There is a change, we know it. So they're really, really small, we can't tell there's a change, but we know there is a change. What do we call that? differential change. It's just a little bit of difference. But there is a difference, so we call it differential change. How do we write differential change? D, and I'm just using, the book uses U for potential energy. I'm just going to use potential energy over ds. Or you can say the derivative of the potential energy as a function of position is the force to do the work. The force it took to do the work. It's the negative of the force. It's the negative force to do the work. Now, you're like, well, you sure about that, Nate? I don't know. I could use gravity, but that's more of a trivial example. Let's look for a spring. So for a spring, we said that the potential, the energy stored in the spring, the potential energy of the spring is 1/2 k x squared. So let's compress a spring. The springs we have. That can really work on your lats up there, probably right here. Compress that spring that we had in lab. If we compress it, we're compressing it a distance. How much force would it take to do that? Well, of course, it's going to be a function of how far we pressed it. But from an equation standpoint, let's see. So the force to do that would be minus in the s direction, but now so that's what it is, but let's do it in the x direction. Let's assume x is horizontal. So the force in the x direction is going to be minus derivative of 1/2 kx squared as a function of x. Now, those of you who have had pre-calculus or taken Calc 1, you've done polynomial differentiation. You can use the derivative formula, f of x plus h minus f of x over delta h and stuff, and that whole big long thing, or you just learn the rules later on that make it simple. That's the definition. You basically take the exponent, bring it down here, put it in front of make it the coefficient, or multiply it times the coefficient, subtract the exponent by 1. That's the simple way to do polynomial differentiation. And if you do that, we get 2 times 1/2, that's a minus. And that x squared now just becomes x to the first power. And I got to put k in there. And 2 times that becomes minus kx. So the force, wait a minute. So the force to compress a spring is minus kx? Geez, that's just Hooke's law. That's just Hooke's law. So from the energy it took to compress a spring, we found the energy it would take to compress it. We found the force to compress it. And that matches what we know. So saying that's a derivative of the potential energy. In this one case, it's valid. If you try the others, it's valid in all the other ones as well. That works out. Simple polynomial differentiation. I may ask you to do something like that on the test, but if I do, it will be very simple differentiation on it. Now, if you want to think of it otherwise, think of it like this. And what I want to say here is that the rate of change of potential energy over, let me say it a different way. I think I can say this a better way. How much the potential energy changes as function, meaning as something happens, of position is the force required to do the work, to make something happen, to move something. So it's how much that potential energy changes as a function of position. All a derivative does is find how much it changes as a function of position. If you remember, hopefully they taught you, hopefully they did, I assume they did. All a derivative is a rate of change. It's a slope. It's just a slope. And how much that slope is, so the x-axis is the function of. Y as a function of x is the way you grab it. So rate of change, derivative, rate of change of potential energy, how much the potential energy changes as a function of position as something moves. That's the force it took to get it done. Okay? If you do a bench press, if you're moving something, if you're pushing up, it takes a lot of force to push it up fast. Well, that's a quick change in potential energy. It takes a lot less force to push it up slowly. I still got to push it, but I'm pushing it slower. That's going to take less force to push it slower. So the derivative, the rate of change of that, of potential energy, because it changes really slow, it's slowly pushed up. If the rate of change is slow, the force is going to be low. I hope that makes some sense. Let's look at conservative and non-conservative forces. All right. Let's look at conservative and non-conservative forces. Make sure you can see that. I'm pretty sure you can. Yeah. All right. Conservative and non-conservative forces. Some of you might hear that and think, oh, he's going to go into politics. No, I don't. I don't do politics in class. In politics, conservative means keep things as they are. In this case, it's a similar type definition, because that's the definition of conservative, not just in politics. If something's conservative, it tries to keep things as it is. But I'm going to say here with conservative forces do not depend on path. You're like, what? What the heck darn does that mean? Does not depend on path. Well, let's get an idea of this. I will say, I'm just going to say it, that gravity is a conservative force. Oh no, I said something political. They're going to put me on Twitter and I'm going to get canceled, right? No. We're just going to say gravity is conservative. What is that saying? That's saying gravity doesn't depend on path. So the energy due to gravity, if it's a conservative force, shouldn't depend on how you get there. It's like, that's crazy. Of course it depends on how you get there. It takes more energy to go down a winding road and get someplace than go straight there, Knight. Come on. Come on, Knight. What you been doing? Getting a little senile? Not yet. Let's do an example of how gravity gives something energy. Here's some masking tape, right? How can I give this masking tape more energy? Well, I could throw it, gave it more energy. But if I do that, that's not gravity. We're just going to look at gravity, okay? So how does gravity give this more energy? It raised it up, got more energy, right? Hit my hand. Do it this. No pain. A little bit of pain. Oh. Lots of pain. Oh. Of course, mega pain. Mega pain. You know. But, of course, the higher up it goes relative to my hand, especially if it's a piece of metal or something, a big metal ring, and if I let it bounce off my hand, it would hurt more, right? Because it's got more energy. That's okay, Knight. You got me there. Yeah, that seems reasonable. But I'm saying path doesn't matter. So what does that mean? I'm saying that this piece of tape here relative to my hand has the same energy if I raise it here, or it has the same energy if I get it there a different way. What if I go woo, 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 or I go wee, 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 take it all the way around, bring it around town, to right there. It's the same place it was before that I just went straight up. Relative to my hand, though, at the end position, does it have the same energy? Of course it does. It's at the same height. So for gravity, height is the only thing that matters with energy, right? MGH. It's not path. Height matters. Height is the only thing that matters. I can get there going straight up, going around town, or I can go the crazy ride. And I still get there, right? Same height, same energy. Path doesn't matter for gravity. All right? That's a conservative force. Now, why do we go about this? Well, conservative forces, and this is where it really starts to matter. Conservative forces conservation of energy is valid for conservative systems. Notice there's a similar root. Conservation, conservative. There's a similar root there. If a system has only got conservative forces, if it's just gravity, distance between the 2 points is all that matters. It doesn't matter how you get there. Now you say, well, sometimes it matters. Here, give me an example of something that's a non-conservative force. Okay. Well, I would say, well, what if I go from this point here, whee, and then I jump to this point here? I've been taking lessons from fleas. You know where they jump real high, fleas will? Okay. So I jump up there, and I get up there, so I've got a certain amount of energy. I have to push against